All right, in concept B, we're going to be looking at how to draw and name various straight chain hydrocarbons. Now, we briefly talked about this in class the other day, where we looked at the different categories of hydrocarbons. We talked about saturated hydrocarbons, which are just alkanes with all single bonds, and unsaturated hydrocarbons that have a double, if it's an alkene, or a triple bond if it has an alkyne. So we can look at a homologous series of hydrocarbons, and this is a group of related compounds in which each member differs from the one before it by one carbon unit. So in your reference tables, you have this chart that you should be looking at as we're doing this so you can gain some of that information, where we have three different series or families of these hydrocarbons. We're able to use the information in the chart to basically draw the various different members of each of the series. Alright, our first one we're going to focus on are alkanes. These contain all single bonds between the carbons. This means that they have to have the maximum number of hydrogens bonded to their carbon chains. And remember, carbons are going to make 4 bonds. So keep that in mind. So here, when we look at the chart, we can see that we have a single bond between the carbons, so that is a clue that an alkane has single bonds between carbons. We're also going to see 2 parts in the name. The part that's most important for us is the ANE. ANE is going to be used to signify any of these alkanes that we're going to use. Now, the general molecular formula for any alkane is CnH2n plus 2. So if I know how many carbons I have, I can figure out how many hydrogens there are. If I know the hydrogens, I can figure out the carbons, or use the formula to match up to the alkane. So for example, if I have 8 carbons, N is equal to 8. So when I plug that in, I would find then that I should have 18 hydrogens. And remember, this is our molecular formula. So our general rule for naming is we're going to use the prefix from table P to tell you how many carbon atoms you have, and then we're simply going to add the suffix or ending of ANE. So this is that table P in case you don't have it in front of you. These prefixes are not something you need to memorize since you'll have them for any test or quiz. Okay, but you should start to get familiar with them just to make it a little bit quicker, and those match up with the number of carbon atoms. Alright, so let's start with our first example, CH4. I have 1 carbon, which means that I'm going to use the prefix meth and then the ending ANE since there are no double or triple bonds between any carbons. Our structural formula is going to be our carbon in the center, and then we fill in the rest of the 4 bonds around carbon with our hydrogens. The next example I'm giving you in your note packet, the structural formula. So here we can see that we have all single bonds signifying our alkane, and we can see that we are saturated with our hydrogens. So if I count up my number of carbons and hydrogens, I have 3 carbons, and then I can count around and find my 8 hydrogens. Or I could use that general formula to come up with the number 8. And then finally, we're going to be looking at using our prefix for 3, which is prop, and then adding on ANE. So propane signifies 3 carbons with all single bonds between them. And then the last example I gave you in note packet is C5H12. Okay, that has 5 carbons in a chain. So pent is going to signify the prefix for 5, and then ANE is because when I go and draw this, I find that I have all single bonds between our carbons. Or I could look at which of the general formulas there are that matches up with the fact that this is an alkane. Alright, one important part is that as molecules get larger, those IMFs increase, they become stronger, so thus there's a higher melting point and boiling point. This is something that you need to know and be able to identify. So again, the larger our hydrocarbons, the higher the melting and boiling point. Alright, now we're going to move on to naming and drawing alkenes. These are hydrocarbons that contain at least 1 double bond, and you can find that in your reference tables as well, and we'll point that out in class. The general formula is CnH2n, meaning that if I have 6 carbons and N is equal to 6, plugging that 6 in, I find that I would have 12 hydrogens. So our general rule is we're going to basically look at our changes of carbons and add the suffix ENE. However, we have to actually count our main carbon backbone or carbon chain and number the lowest number that possible on the double bond. And I'll talk about what this means. Remember, our prefix is still going to refer to that straight line number of carbons. You must start counting the carbons from the side that the double bond is closest to. So here, this is kind of a skeletal structure of this compound. Each of the corners represent a carbon. So when I count, the double bond is closest to my right end, so I'm going to start and place a 2 on our double bond. And then we would number the rest of the way. So again, I'll point that out in a couple of these examples. here, before we do not draw this in your notes, if we're counting from the left and we're looking at this double bond in our alkene, we can see that it falls on the fourth carbon. However, if I draw from the right, I put a lower number on a carbon with the double bond. So we would want to, again, in this case, go from the right because of the fact that 3 is lower than 4. All right, so for this first one, we have, in this explanation is just pointing out where these parts come from. You don't need to have that in your notes. Our structural formula has 2 carbons, so that's where the F prefix comes from, and then there is a double bond present, so we have our ENE. Now, what happens when we get up to more carbons is that we need to include a number, because that double bond could exist in 2 different places within our structure. So the but still stands for 4 carbons in our chain. ENE represents that double bond, and then I had to number in order to make sure that I'm placing my double bond in the correct spot. So by numbering from the left, because my double bond is closest to the left, it's on the first carbon, so the 1 is representing that the double bond starts on the first carbon. And then here I gave you a little interesting example. This is a little bit different because I have 2 double bonds present. So instead of just adding ENE, I add in a diene instead. So our penta represents the 5 carbons in our chain. Diene represents that we have 2 double bonds. And then the numbers out in front represent where those double bonds are along my 5 carbon chain. So my double bonds are closest to the left-hand side, so I started numbering from the left. So my first double bond started on the first carbon, and then I had 1, 2, 3. When I get to the third carbon, my next double bond begins. So the 1, 3 is representing the 2 spots that those double bonds are located. And one thing I want to point out is commas are always used between numbers, and dashes are always used between a number and a letter. All right, and then our other example I want to go over with these alkenes is 2-pentene. Okay, we have 5 carbons here, so I have the prefix for pent. We have a double bond present, so I have ENE, and then I place a 2 out in front to represent where that double bond is located. So it's the second carbon in. All right, and then finally alkynes. This contains a triple bond somewhere along the carbon chain. Our molecular formula for this is CnH2n-2. So if we plug in 4 carbons, we find then that we only have 6 hydrogens present. All right, our general rule is going to be very similar to the alkenes. We need to number our carbon chain if necessary, use our prefix to refer to the number of carbons, and then add it on the ending YNE instead of ANE or ENE to represent that triple bond. So same thing, we want to make sure we count from both sides in order to come up with the right number. So for the structure, we would have 2-heptyne, because I have 7 carbons, and then counting from the right-hand side, which my triple bond is closest to, I get to the second one. So here we have propyne, the prop representing the 3 carbons, the YNE representing the triple bond. There's no number needed because whether I put the triple bond there or I put it between these 2 on the right, it's always going to end up on a first carbon, so it's unnecessary to show the 1. So here we have 2-butyne, we have 4 carbons. We have the YNE ending to represent a triple bond, and that 2 is representing the fact that that triple bond is on the second carbon on either side that I happen to count in from. And then 2-pentyne, this is just the case where we now have 5 carbons. Again, in this case I wanted to start numbering from the right because that's where the triple bond is closest to. So that 2 is representing the triple bond that falls on the second carbon within the 5 carbon chain. All right, so you can get rid of that 4th box in that chart in your notes. So isomers are molecules, and we start talking about isomers now because you're going to see a lot of different similarities and things that we're going to be doing in class between different molecules with our alkanes, alkenes, and alkynes. Isomers are molecules that have the same molecular formula, so they have the same number of each element. That means they have the same GFM and the same percent composition for each of their elements. However, they have different structural formulas, which means they have a completely different arrangement of elements. So while they have the same maybe carbons and hydrogens, if we're talking about a hydrocarbon, they're arranged differently. So this difference in arrangement causes different physical and chemical properties. So while they have the same number of each element, their structural formulas are different, so everything else in terms of their properties is different. So if we look at these 2 isomers of butane, they both have the molecular formula of C4H10. However, this one is a straight chain of our 4 carbons, and the one on the right we say will have 3 carbons in a chain and a branch of a methyl group, which we'll talk about more on Monday. So which of the 4 structural formulas are isomers of each other? So what you would need to do is go through each, count up the number of hydrogens, carbons, and oxygens in this case. So I would write down each of their formulas. And then while they all have different structural formulas, we find that A and B have the same molecular formula. So it's really just that with isomers that we're going to be talking about. One thing I want to note is that the more carbons a molecule has, the more possible isomers are can be formed. So it's almost like the more puzzle pieces you have, the more combinations you have. Same thing with the number of carbons. All right, so I know that was a lot of information about these straight-chain hydrocarbons. We're going to work on the reference tables tomorrow and make sure that you are all set before moving on.